What if the future of refrigeration doesn't require harmful gases, doesn't need noisy compressors, and could slash energy consumption across the globe? What if the next revolution in cooling technology isn't hidden inside a chemical formula, but inside a magnet? For more than a century, refrigerators have worked in essentially the same way. Compress a gas, expand it, move heat from one place to another. Simple, effective, and incredibly common. But what if there was a different way? A method that sounds almost impossible. A method where cooling comes not from chemicals, not from compressors, but from magnetic fields. It sounds like science fiction. After all, magnets attract metal. They don't make ice. Or do they? Because deep inside certain materials lies a strange phenomenon that has fascinated scientists for generations. A phenomenon so powerful that researchers believe it could completely transform refrigeration, air conditioning, industrial cooling, medical equipment, and even future space missions. It's called the magnetocaloric effect, and it might change how the world stays cool. Today, we're exploring the incredible science behind magnetic refrigeration, how magnets can create cold temperatures, why major companies and researchers are racing to perfect this technology, and whether your next refrigerator could be powered by magnets instead of traditional cooling systems. The future may be colder than you think, and it might be magnetic. To understand why magnetic cooling matters, we first need to understand how refrigeration works today. Every refrigerator in your kitchen is essentially a heat-moving machine. Contrary to popular belief, refrigerators don't create cold. They remove heat. The process relies on refrigerant gases circulating through a sealed system. The gas is compressed. Pressure rises. Temperature rises. The heat is released. The refrigerant expands. Temperature drops. Heat is absorbed. And the cycle repeats endlessly. It's a brilliant invention, but it comes with problems. Lots of them. Traditional refrigeration consumes enormous amounts of electricity worldwide. Air conditioners and refrigerators collectively account for a significant portion of global energy demand. As populations grow and temperatures rise, cooling needs are expected to skyrocket. Some estimates suggest the number of cooling devices worldwide could triple by mid-century. Think about that. Billions more refrigerators, billions more air conditioners, billions more systems consuming energy every second. Then there's a refrigerant problem. Historically, some refrigerants damage Earth's ozone layer. Others contributed heavily to global warming. Modern refrigerants are far better than their predecessors. Yet many still have environmental impacts. Scientists began asking an important question. Could there be a cleaner way, a quieter way, a more efficient way? The answer may have been hiding inside magnets all along. Let's perform a thought experiment. Imagine holding a special metal. Nothing unusual happens. Now imagine placing that metal inside an extremely powerful magnetic field. Something remarkable occurs. The material heats up. Remove the magnetic field. The material cools down. No gas, no compressor, no chemical reaction, just magnetism. At first glance, this seems impossible, yet it's real. This phenomenon is known as the magnetocaloric effect. Discovered in the late 1800s, it remained mostly a scientific curiosity for decades. The effect occurs because atoms behave like tiny magnets. Inside magnetocaloric materials, countless microscopic magnetic moments point in random directions. When a magnetic field is applied, many of these tiny magnets suddenly align. Order increases, entropy decreases, energy shifts, the material warms. Remove the field. The tiny magnets become disordered again. The material cools. This heating and cooling effect forms the foundation of magnetic refrigeration. The challenge is learning how to harness it efficiently. And that's where things become fascinating. Here's where magnetic refrigeration starts feeling almost magical. Imagine a special metal moving through a powerful magnetic field. Step 1. The material enters the field. Its temperature rises. Step 2. Heat is transferred away. The material cools back to normal. Step 3. The magnetic field is removed. The chilled material absorbs heat from a refrigerator compartment. Repeat the cycle continuously. And suddenly you have refrigeration. No conventional compressor. No traditional refrigerant cycle. Now the material becomes colder than before. Step 4. Just carefully control magnetic fields and specialized materials. Scientists often compare it to a thermal pump powered by magnetism. The system continuously moves heat from one place to another, exactly what a refrigerator needs to do. But there's a catch. Actually, several catches. And overcoming them has taken decades of research. For years, magnetic refrigeration remained largely theoretical. The magnetocaloric effect existed, but it wasn't strong enough. Scientists needed materials that exhibited dramatic temperature changes when exposed to magnetic fields. Then came a breakthrough. Researchers discovered certain rare earth alloys produced much larger effects. One material, in particular, generated excitement. A metal called gadolinium. Gadolinium became something of a superstar in magnetic cooling research. Near room temperature, it demonstrated an unusually strong magnetocaloric effect. Suddenly, magnetic refrigeration looked far more practical. Scientists began experimenting aggressively. New alloys emerged. Gadolinium silicon compounds, lanthanum iron materials, manganese-based compounds, each offering unique advantages, each bringing researchers one step closer to commercial reality. The hunt for better magnetocaloric materials continues today because the stronger the effect, the more practical magnetic refrigeration becomes. You might be wondering something. If magnetic refrigeration requires powerful magnetic fields, wouldn't generating those fields consume massive amounts of electricity? Surprisingly, not necessarily. Enter one of the greatest advantages of magnetic cooling: permanent magnets. Modern rare earth magnets are astonishingly powerful. Some are strong enough to generate magnetic fields without continuous electrical input. Once manufactured, they simply remain magnetic, day after day, year after year. This means magnetic refrigeration systems can often use rotating magnet assemblies rather than energy-hungry electromagnets. Imagine a wheel of powerful magnets spinning around magnetocaloric materials. As the materials move into and out of magnetic fields, cooling occurs naturally. The system becomes remarkably efficient and often much quieter than traditional compressors. No loud mechanical pumping, no constant vibration, just smooth magnetic cycling. So why is everyone suddenly interested? Because magnetic refrigeration offers several potentially enormous advantages. First, efficiency. Some studies suggest magnetic cooling systems could exceed the efficiency of conventional refrigeration technologies. Even modest improvements could save tremendous amounts of energy globally. Second, environmental impact. Magnetic refrigeration may significantly reduce or eliminate reliance on traditional refrigerants. That means fewer greenhouse concerns, fewer leaks, and potentially safer cooling systems. Third, noise reduction. Compressors are noisy. Magnetic systems can be dramatically quieter. Fourth, reliability. Fewer moving parts often means less wear and tear. Potentially longer lifespans. Potentially lower maintenance. When researchers add up these advantages, the implications become enormous. It's an elegant solution, and engineers love elegant solutions. We're not just talking about refrigerators. We're talking about supermarkets, data centers, hospitals, laboratories, electric vehicles, industrial facilities, even spacecraft. Anywhere cooling is required, which is practically everywhere. One of the most exciting possibilities lies inside data centers. Every internet search, every stream movie, every AI model, every cloud service depends on computers. Computers generate heat, lots of heat. Data centers spend staggering amount of energy simply keeping equipment cool. As artificial intelligence expands, cooling demands are increasing rapidly. Magnetic refrigeration could become an attractive alternative. Higher efficiency means lower operating costs. Lower power consumption means reduced environmental impact. And quieter systems improve working conditions. Some researchers believe advanced cooling technologies will become just as important as faster processors in the coming decades. Because no matter how powerful a computer becomes, it still has to stay cool. If magnetic refrigeration is so promising, Why isn't everyone using it already? Because reality is complicated. The biggest challenge is cost. Many powerful magnetocaloric materials rely on rare earth elements. These materials can be expensive. Then there's manufacturing. Traditional refrigeration has benefited from more than a century of refinement. Factories, supply chains, technicians, infrastructure, everything already exists. If magnetic refrigeration is so promising, why isn't everyone using it already? Because reality is complicated. The biggest challenge is cost. Magnetic refrigeration must compete against an incredibly mature industry. Another challenge involves temperature range. Creating cooling is one thing. Creating large temperature differences efficiently is another. Engineers continue searching for materials that perform better across broader operating conditions. Then there's scalability. What works beautifully in a laboratory doesn't always translate into mass production. History is filled with technologies that looked amazing in prototypes but struggled commercially. Magnetic refrigeration must prove it can overcome these hurdles. And that's exactly what researchers are working on. Around the world, laboratories are pursuing the magnetic cooling revolution. Researchers in Europe, North America, Asia, and beyond, universities and private companies are investing heavily in next-generation cooling technologies. The competition is intense. Every percentage point of efficiency matters. Every manufacturing improvement matters. Every material breakthrough matters. The first company that successfully commercializes highly competitive magnetic refrigeration could reshape a multi-billion-dollar industry. And industries of that size rarely stay unchanged for long. History shows that disruptive technologies often appear slowly. Then suddenly, could magnetic refrigeration be approaching that moment? Many scientists think it's possible. Picture a future kitchen. You open your refrigerator. It's quieter, more efficient, environmentally friendlier. Inside, there are no conventional compressor systems. Instead, magnets silently move heat away from your food. Now expand that vision. Entire grocery chains cooled magnetically. Hospitals using magnetic refrigeration for sensitive medical storage. Massive server farms reducing energy consumption. Electric vehicles with more efficient climate control. Space missions relying on ultra-efficient cooling technologies. The possibilities extend far beyond household appliances. Because cooling is one of civilization's invisible necessities. We rarely think about it until it's gone. Yet cooling influences food preservation, medicine, computing, transportation, manufacturing, and countless other aspects of modern life. Any improvement reverberates across society. That's why magnetic refrigeration matters. It's not just about a better fridge. It's about a better cooling infrastructure for the entire planet. Magnets have always seemed mysterious. They pull, they attract, they repel, yet hidden within their invisible forces may be a technology capable of transforming one of humanity's most important inventions, refrigeration. From the strange physics of atomic alignment, to the magnetocaloric effect, to advanced materials engineered at the microscopic level, magnetic refrigeration represents a remarkable intersection of science and engineering. Will it completely replace traditional refrigeration? Nobody knows. Perhaps conventional systems will continue evolving. Perhaps magnetic cooling will dominate specific industries. Or perhaps a hybrid future awaits. What we do know is this: the demand for cooling is growing. The need for efficiency is increasing. And scientists continue discovering new ways to harness the extraordinary properties of magnetism. The next great refrigeration revolution may not come from chemistry. It may not come from compressors. It may come from a force humans have been fascinated by for thousands of years. A force that quietly shapes our modern world. A force that might one day keep billions of people cool. A force we simply call magnetism.